I'm delighted to introduce our next speaker, Dr. Will Roper. The Honorable Dr. Will Roper is currently a distinguished professor at Georgia Tech, focusing on technology impacting national security. He's a board member and advisor of numerous startups and investment firms, a senior advisor at McKinsey, and honorary group captain in the UK Royal Air Force. Will previously served as Assistant Secretary of the Air Force, leading over 60 billion of annual technology development and operations for the US Air Force and Space Force. During 15 years of national security service, Will received the Pentagon's highest award for public service. He holds a bachelor's and a master's in physics from Georgia Tech and a doctorate in mathematics from Oxford University, where he studied string theory as a Rhodes Scholar. Dr. Will Roper, thank you for joining us.
Hello, everyone. I hope that you are having a great session and a great day. My name's Will Roper, and I've done a variety of jobs, most of them inside of the government. All of them had something to do with artificial intelligence, at least in recent years. But I'm here to talk to you about the future of artificial intelligence. And I want to share some of the things that had me really excited, especially as I departed the government as the acquisition executive for the Air Force and Space Force, and share how I've been able to follow up on them now that I'm in the private sector. It may surprise you in a talk on artificial intelligence that the thing that gets me really excited is its application to hardware. Hardware did not eat the world when software did, but it looks like this is finally going to change. And I'll share a few insights as to what I've seen both in and out of government about what happens when we can start applying artificial intelligence to systems where physics is involved. Now, it'll probably help you to know a little bit about my background before we start talking about the future. And we also need to talk about a trend that's happening both inside of government and in private industry called digital transformation or digital engineering, and why it's such a big deal and will cross paths with machine learning and AI and lead to a pretty awesome or pretty scary future, depending on whether you're an optimist or a pessimist. And I'll share why. So I've worked a variety of jobs inside of the government. I did not intend to go work my career there. I was a string theorist at Oxford and realized one day that I was a pragmatist and wanted to work on problems that I would know if they were valuable during my lifetime. And I thought about where that would be, what field I would be able to do that in. And I had a lot of advisors tell me that the U.S. government is a great place to make a difference. It's challenging, but there's a need for technical leaders inside. And so I ultimately took that advice and started working at MIT Lincoln Laboratory and learned a lot about defense. They were kind enough to take me under their wing and really teach me all different facets of the military. And then I started at Missile Defense Agency as their chief futurist, thinking about how missile defense could be now and in future. That was the first role where I was in both a technical role and a futurist role. Very interesting that you're almost like a science fiction writer, except you're responsible for making the science fiction fact. The first thing you have to do is dream it. But you have to dream it in a way that's technically achievable. And over time, I built an instinct for that. What would be the next big thing that we could go build and demonstrate and make the new fact? And during that time, I got to know Ash Carter, and he asked me to come work for him when he was the deputy secretary and later as the secretary, running what was a classified innovation office that I started called the Strategic Capabilities Office. And that took this futurist role and put it on steroids. Rather than just doing it for missile defense, I was doing it for every facet of the military, looking at the future of peer competition and high-end warfighting. And it was an amazing, challenging job, but also amazingly rewarding, because I got to work with all of the military departments. Well, if you have a task that big, you're running around the world of technology, both inside of the government and the research labs, and outside in private industry where so much of innovation is happening. And you're looking for technologies that are mature enough to apply so that you can create that science fiction vision that you go make science fact. And that was where I first crossed paths with machine learning. This was very early on. The Pentagon was still focused on violent extremism and the challenges of that mission. It had not pulled its head up and thought to the future of competition with China and Russia and the needs to be more strategic and long-term in its focus. I had that job before anyone did. And so I learned about machine learning before it was public knowledge in the Pentagon, and it seemed a lot like previous programs that tried to do automatic target recognition in the 80s and 90s that failed miserably. But thanks to a lot of great experts in private industry, including those companies like Google, I learned that no, this really was different, that machine learning was now able to do what we had called automatic target recognition, but do it at a high level of reliability because we had access to numerous data sources that were not available to us in the past. And of course, compute has gotten better and better year after year. And now computer vision could now be better than the best analysts that we had inside the government if we were looking at high volumes of data. And I thought, well, this is fantastic for warfighting because we had information overload on the battlefield. We are streaming data from so many sources, putting it in front of operators, many of whom would be in harm's way and asking them to make critical decisions. That doesn't seem like a good idea if we can create a smart filter using AI to choose the targets that they should look at and the ones that they don't need to. And so I proposed a program called Project Maven that ended up becoming of some import and fame. And thanks to my boss at the time, Secretary Bob Work, after Ash Carter moved up to be the SecDef, that program got funded and I initiated Maven, ultimately partnering with USDI, the intelligence arm of the Pentagon, to make it an intelligence program. And well, you know what happened to Maven down the line, but that's not the point of this story. That was a period where we had to take tutorials on machine learning to Pentagon leaders to tell them this was different. This was something that what is not a if it happens, it was happening. It will continue to happen in private industry. And if we don't leverage it, we'll be left behind. It's amazing to see how far the Pentagon has come since that time, and yet how little it's accomplished in actually unlocking machine learning on the battlefield. But I remember those days. It would have been in around 2000, maybe 15 or 16. So very, very early on in my days working at the SecDef. Well, we ended up applying machine learning to quite a few defense programs. It became kind of the thing you did when you were doing defense programs. If you were generating data of any source, you should have some machine learning component helping you be smarter in making decisions about that data without having to have people be involved. It just became status quo for us. Now, I'm going to come back to this thread, but I think it's worth sharing with those of you who are not as familiar with government, why from those early pathfinders, why has it been so challenging for the Pentagon to unlock machine learning? And it's really that the infrastructure isn't there. The cloud data streaming, high bandwidth transportation layers that we are all enjoying and using right now to do this talk are really absent in many places in the Pentagon. So one can do a demonstration on machine learning and show its viability and import for national security, but scaling it to an enterprise level capability that can be used around the world, the Pentagon is just not equipped for that. It still thinks of itself and aligns itself in terms of platforms, physical systems that people operate. It's not very good at information age technology and has continue to stay behind the power curve, adopting technology that is available and ready to be used thanks to private industry, but for some reason has a difficult time fitting inside of a Cold War era procurement system. So it's a shame that as we do this talk, we're on devices that allow us to communicate together. We can touch things around the world, at least touch them digitally. In some cases, create physical effects on objects that can be hundreds of miles away. We are tremendously empowered as we sit here today. But the average person in uniform leaves that world of personal digital empowerment and goes into a job in the military where they're in a digital backwater, behind the times, touching almost nothing, where information is still, for the most part, exchanged by people talking to people. Hopefully, at some point, the Pentagon will realize that its information technology and infrastructure that supports it is a warfighting system. And if you don't treat it as one and your adversary does, you will lose because of that warfighting system facing you on the battlefield. Let's push a pin in this part of the topic. It's been well talked about. The fact the department has not made investment in IT. It has not become digitally native. It lacks the software expertise. And I worked really hard in the Air Force and Space Force to try to fix that by doing enterprise-wide cloud, software factories like Kessel Run and Kobayashi Maru so we could build up coding skills, and then finally adopting new technologies like Kubernetes that allow us to move code from our development environments out to the edge where it needs to operate on the battlefield. And we even used publicly available algorithms to develop, to train an AI co-pilot for the U-2 and demonstrated that not only could we put that AI in charge of the U-2, that we could push live software updates to that aircraft in flight, none of which had ever been done before. So we tried to fix this problem. And I think if that was the end of this talk, it'd be kind of a downer, right? All of this promise on the outside, yet so very little adoption on the inside. But there was another trend that I was not aware of when I was in the Air Force and Space Force, but became aware of and got me super excited because it seemed like a similar transformational capability for hardware. And what I didn't realize, though, is how the story ended. So that enabling technology was digital engineering. And that term isn't even stable yet. Terms are still evolving. So if you've approached the topic and heard it called digital transformation or digital engineering or industry 4.0, it's still a very much evolving topic. If you don't know anything about it, don't worry. It's still fairly nascent, though moving very quickly. So let me give you a summary of what it is and how I learned about it. So digital engineering is pretty much what it sounds like. It's doing engineering digitally. And that probably sounds like, well, so what? We've been using computers to do engineering since computers began. That's why computers were created, originally to calculate Army ballistic trajectories. We've been using them to help us with physical systems since a computer was conceived of. What is different in digital engineering? That's very similar to the difference between the old automatic target recognition programs of the past versus the machine learning of today. It's the same idea that we can do engineering digitally, but the enabling technology has become so good that new things are possible that simply weren't in the past. It is possible today to fully digitally design, test, and certify systems without having to physically build them. Now, how does that happen? It happens because computer models and simulations are capable of creating the physics and structures to such a high degree of reliability that physically building the asset and physically testing it is just recreating data that we already know is valid in the model. The model is just as much a source of truth as physical testing and prototyping. Well, that's an amazingly enabling technology, given that hardware is often expensive and slow and has environmental impacts to build. This solves all three of those at one time. And I became aware of it due to programs like the T-7 in the Air Force and Ground-Based Strategic Deterrent and others that were adopting digital transformation. And I did my best to make it an enterprise-wide approach that we would take. I got taken under the wing of the McLaren racing team in the UK, who taught me that the way they do digital engineering makes the way we build airplanes look like a thing from the Neolithic age. They're designing tens of thousands of digital cars per season. They're changing every 15 minutes of every day. And by the time a racing season ends, the car that finishes is 85% different than the car that began. And the car that began the season wouldn't even qualify for the last race. Tens of thousands of cars changing every 15 minutes, evolving. Wow, it's just an inspiring level of digital agility. It makes the way that we do aviation and spacecraft building, where we have a design and we go often into mass production and don't change the system for years, sometimes decades. That looks like a losing strategy. So it really looks like this agile approach to software starting to come into hardware. And I'm super excited about it. I wrote about it, used the Matrix movie as a way to try to inspire our team, saying, the Matrix was a science fiction movie that said, one day a digital reality could actually be a reality. This is a piece of that, saying that a digital engineering reality is becoming a reality for creating new technologies. And it can be harnessed with that same kind of science fiction flair. It can be harnessed for science fact today. And many programs did. And I will say that when I left the Air Force and Space Force, I was still really focused on the hardware benefits of digital engineering and digital transformation. Being able to design things really quickly, good. Being able to design things quickly, good. Being able to physically produce them, having de-risked things that normally required learning curve ramps, like learning to assemble, learning to operate, learning to maintain. You can now learn to do these things digitally, so that when you do them physically for the first time, you're already good at them. Good. Most of the value that I was seeing at the time and imagining at the time was being able to take something that would have occurred in the physical world, turning it into software via models and simulation, learning in those models and simulations and design tools where it's cheap to learn and change and improve, so that by the time I'm putting in the effort and resource to do the physical counterpart, I know I'm good at it. It seemed like that was a thing that we should unlock for defense programs. We'd be faster, we'd be cheaper, we'd be more agile and innovative. All of those things are true. All of those are reasons to go do it and to do it with gusto. But what I've realized since leaving the government and finding myself in a variety of roles consulting with McKinsey and Company and others is that the things that we did in digital transformation in the Air Force and Space were some of which were groundbreaking. And so companies that had heard about them through various communications channels reached out to me and said, we'd like your help on digitally transforming. Help us do in our company like what you helped programs do in the Air Force and Space Force. And so I said, yes, this is a great way for me to continue learning, because every program that took on the challenge, I learned something. They would push the tradecraft further. And so it was very interesting working with companies inside and outside of defense, helping them scale this digital mountain. There's one company that's in the public domain and has some pretty awesome videos, which I highly encourage you to go check out. And that's Team New Zealand's America's Cup team. And they used digital engineering for something that's pretty amazing and would be hugely impactful on the battlefield and also hugely scary if your adversary had it and you didn't. Not only did they build a complete digital engineering ecosystem for sailing, meaning they have a representation of the water and the wind and all of the physics associated with it and the structure of the boat, everything that's needed to create an ecosystem of competitive sailing that is equivalent to reality within acceptable error terms. They did something else. They used it to train an AI to sail. And that AI not only eclipsed sailing like humans, eclipsed sailing like humans against humans. It became a better human type sailor than any human has done. So it started sailing differently than humans have ever sailed. It learned techniques that have never been part of sailing wisdom. And ultimately, the position flipped. The human team relearned to sail from the AI. Something very similar to what's happened with chess and Go, with AlphaGo Zero and its successors, becoming better than any human has ever been and ever will be. And the best human players now learning or relearning chess and Go from the AI. This has happened for arguably the first time in an area of activity that requires an understanding of physics and structures. Chess and Go are games, so they're mathematical concepts. We don't need a representation of physics for the AI to understand them. And so we can use digital means to provide AI with an abundant source of relevant data to train. Well, this had a big impact on me because it told me that once you've done this digital engineering ecosystem, also called a digital thread, not only does it do all of the amazing things that we've discussed, reducing costs, speeding things up, allowing you to train before the physical thing exists, lowering environmental impact, it does all of those things. But finally, for the first time, it provides AI an abundant source of truthful data to learn and master physical activities. And I had seen a hint of this when we were training the U2 Copilot. There was no way to train that algorithm by flying in the physical U2. We couldn't explore all of the corner cases that are needed to be a proficient U2 Copilot. We had to do it via simulations. That was the only way to generate an abundant enough source of data. And then I saw this again replicated in a completely commercial endeavor, competitive sailing. The same thing, that digital engineering ecosystems, digital threads, not only changed the engineering of hardware, they gave AI access to a source of data so abundant that the AI could learn and understand physical things. And that's what has me really excited about the future of AI and also really scared. Digital transformation is going to happen in every industry that deals with physical things. There are just too many incentives that are stoking this fire, speeding things up, reducing cost. It will happen. And I'm doing everything that I can to help speed up that transition because of all of the benefits we've mentioned. But hand in hand with it will come the ability to let AI finally crawl out of the internet and learn the world around us. So chess and Go have already fallen, where humans will never be the best beings on Earth, if we'll call the AI a being. Competitive sailing has now joined. Who knows what's next? If you're coming to this talk from a government perspective, almost everything I can think of on the battlefield seems like it can be gamified. And if it can be gamified, it can be understood through discrete means. If it can be understood through discrete means, give AI a rich enough data source to explore the full phase space of battlefield scenarios, it will quickly become better than any human has ever been. Well, I started this talk talking about my journey to understand the power of machine learning and AI through my journey through the government and why the government is still having a tough time unleashing it at scale using machine learning and AI as it exists today, with information technology as it exists today. And now I'm ending by sharing that the future is going to get much faster and much worse. Not only will we have to master AI and machine learning as it is today, we will have to build digital engineering ecosystems, digital threads of every aspect of what we do in the military, or if you're here from private industry, whatever the equivalent is for you, your industry. You'll have to have both, because when you put them together, you get the benefit of starting to teach machine learning what you do in the physical world. And if competitive sailing can fall to AI, I think anything that humans do can. And the future will either be exceptionally hopeful or exceptionally dreary. If this trend is driven by countries that share the values we have today, that this can make the world a better place as AI learns things that humans wouldn't discover to make the world increasingly more optimistic. But this would be a powerful, powerful tool under authoritarian control. So as I look ahead, I hope that the future that we move into is the one where the optimistic door opens, the impossible becomes possible. And if you are on that side of the fight, then you have my thanks, and I wish you Godspeed.